Okay. Starting today's class, we had a bit of a gap in the last week because I was a bit ill. So today in today's class, we're going to see the discussion for the working energy part chapter, and also preferably, most likely, if we can manage time, we're going to go for the elasticity chapter as well. So first of all, with the working energy part chapter, we have almost nothing that is new for AS level, except for there is one small formula that is work done on a gas. But the mathematics relevant to the work energy part chapter would require some significant bigger thinking. Diagonal motion can be involved. Conversion of GP to K can have a lot of individual unknowns within the scenario. The preferable choice for the H equals to 0 or the ground value for GP calculation, that can also be a factor. So I'm going to discuss all of these parts for individual question related problems and also for some other problems as well. So the first thing we have in the work energy power chapter, let's think. Work energy power. You all know the basic definition for work energy power. Work is given by F into X, where X is the distance covered, displacement made in the direction of the force. If there is a bit of an angle between force and the displacement, in some cases that can be also written as Fs cos theta, where S is the displacement and cos theta is the angle between the displacement and the force. So the reason we go for the cos theta part is something like this. Let's say here we have an object and we're applying a horizontal force onto the force like this, but somehow the object was placed on an inclined plane which was in this orientation, and the application of force, let's say it produces angle theta with the plane, and the object moves along the plane in this direction by the application of F force. So throughout this entire journey, while the object moved from this position to this position, it moved by S displacement. We applied the F force, constant F force, which was responsible to move it upwards. And in that process, let's say this much is our horizontal distance covered, or this is the component of displacement which was happening in the direction of force. So in this case, work done can be given by Fx, and if we go for trigonometry over here, there's a 90 degree. We can write x by s equals to cos theta, and therefore x equals to s cos theta. And if we can replace this value over here, we can also get work done can be given by Fx or Fs cos theta. So that's one thing. Energy is basically the ability to do work is called energy. That's one way to define energy. Energy is basically one of the very important quantifiable property of the entire universe. Whenever the way we actually talk about energy can have a lot of different forms. You have come across these names in your O levels. We can have thermal energy, we can have light, we can have vibration energy, we can have attraction forces like van der Waals attraction forces, electrostatic attraction forces, magnetic attraction forces, gravitational attraction forces. We can have potential energy due to the forces that exist between objects. We can have kinetic energy because of the object's motion. We can have energy in the form of electromagnetic waves, which is also electromagnetic waves, which can be considered in some sort of photons sometimes. We're going to talk about photon in our waves chapter after a while. So energy can be available in a lot of different forms, and energy is interconvertible. For the macro world, or the way macro world in the case, I mean that for Newtonian mechanics part, I mean we are not considering that case for subatomic situations. Mass and energy are considered to be two conserved quantity for regular life experiences. So unless we are going across some nuclear changes, it might be fusion, doesn't matter. But unless we are going through some nuclear changes, as long as we do our process within the same atomic structure, so we have the same number of atoms that we started, ending up with same number of same atoms at the end of our process, then mass and energy would be individually conserved. However, in nuclear processes, mass and energy are interconvertible properties, for using the formula E equals to mc squared, the very famous formula of Albert Einstein, which was derived from the second relativity second theory of relativity, the second theory of relativity. This equation gives us the conversion ratio between energy and mass. However, for nuclear reactions, we usually use a new quantity, which is called mass energy, which actually goes on to merge the total mass and energy together as a single expression. So we do not simply consider the mass of an object, we do not simply consider the energy of an object. Rather, combining both the properties, we define a new quantity, mass energy of a certain object or multiple different objects. Within a nuclear reaction, the mass energy altogether is kept conserved, which means you can have a proportional conversion from mass to energy, you can have a proportional conversion from energy to mass. That proportional constant is actually c squared, which is the square of the speed of sound. But that's that. However, we are not going to deal with mass energy calculation for our S level. We're going to talk about this type of nuclear energy and those kind of scenarios in our A2 level in the nuclear fields that we have over there. For our scenario up to our S level, we're going to only deal with scenarios where energy is a conserved quantity and also mass is also a conserved quantity. Which brings us to the concept that the idea of law of conservation of energy, which tells us that energy can be only created, energy cannot be created or destroyed. It can be only converted from one form to another form, which is not a true law for all cases, but for most of our experience scenarios, it is a true law. So although it's not applied everywhere, but we're gonna consider it almost everywhere for our experience world. The other important thing that we have to consider that power can be expressed as F into V. I have actually showed you this expression a bit earlier. This is the power expression for power. This actually can be divided into a much more simpler form. If we can write that, the idea for this equation of power is applicable that if we have an object which is moving at v velocity, and to maintain this v velocity, if we have to keep on applying a constant F force. So try to understand, an object is moving at v velocity, and to maintain that constant velocity v, we have to continuously apply F force. So try to understand the statement over here. We are aiming to maintain a constant speed or constant velocity, but to maintain that we have to continuously apply a force, which essentially means that there must be an opposing force which should be counteracting this F force. So it basically means that whenever the object is going in this direction, there must exist an equal and opposite force of F, which is happening from some other scenario. Usually this can be for the case of resistive force coming from air resistance or some sort of fluid resistance. This can be for some other type of scenarios as well. There are some quantum scenarios where this can be also applicable, but I'm not getting to that. However, if it so happens that to maintain a constant velocity of v, we have to apply F force on an object, then the power required to maintain that velocity is given by F into v. This equation can be also utilized for differentiate form, or for example for instantaneous time. For example, let's say if an object has changed velocity, and then we can find out the instantaneous power at any instant of time by multiplying the force applied on the object with the instantaneous velocity of that point exact time frame as well. So we can have different values of power for different instances of time, which brings us to the idea of a changing force, which is not very important for your syllabus. So we're going to consider for our syllabus, for the sake of simplicity, that whenever we are going to use the equation F equals to F into V equals to power, we're going to consider that an object is trying to maintain a constant speed or velocity v, for which it requires a continuous F force applied onto it. And in that case, the physical power required to make that motion possible is given by F into V, which can be very easily converted into power expression. For example, F can be written as F, V can be given as D over T, and I can write F into D over T. F into D basically represents the force in distance. In this case, I'm representing that the force and the velocity both are in the same direction, not at some angle. If it has some angle, then the power equation would not be applicable. For example, a circular motion moving object, even though it is continuously experiencing a force, but it wouldn't experience a power because the velocity and the force are always perpendicular to each other. So practically there is no displacement happen at any point of time in the direction of force. The force works towards the center, but the object moves tangent with the circle. So the object never, ever, not for even a small fraction of second, ever moves in line with the force. It always moves perpendicular to the force, so there is no work done. So which basically gives us work done over time, which ultimately can give us the expression for power right over here. So that's another scenario that we have. The other thing that is important is actually mostly time, so problem solving. There is one additional formula that we have within our syllabus for the case of work done on gas constant pressure. Actually, the utilization of this formula is actually more vividly used in A2 syllabus, where we actually go for the ideal gas equations and their individual implications and formula and everything. But it's for the case of for the sake of calculation and for a bit of an introduction of the ideal gas scenario, this equation is exclusively introduced in our AS level. So it's important that you learn this equation. This is actually pretty simple. Let me give you a very simple example for this. Let's say we have a cylinder over here, and within the cylinder we have a piston over here, a frictionless piston, and the piston is held over here by nothing. So there is only atmospheric pressure, and inside we have some trapped gas right in here. So this is the trapped gas that we have. So if this cylinder is perfectly stationary, if this piston is perfectly stationary, this essentially means that the inside pressure from the gas, Pg, is exactly equal to the outside pressure from the atmosphere, which is Pa. So if both the pressures are perfectly equal, we can say that but there is an equilibrium. That's why the cylinder is perfectly stationary. Now we can do two types of things. First of all, if we want to compress the gas, we can apply some force onto this piston and try to push this cylinder inward. So let's say if we bring the cylinder inside, then the gas would experience some amount of compression. The gas wouldn't like to experience this compression because the gas has a certain amount of kinetic energy and they're producing a certain pressure. By Boyle's law is applicable for at constant temperature. When temperature is constant, pressure of a fixed amount of gas is inversely proportional to volume, which means whenever we're going to try to squash the object in, the pressure inside the gas would increase. And pressure is also given by force into area. Here the area is constant because the piston is not getting bigger. So if we're trying to push in, automatically the pressure is going to go high, which essentially means the force is going to go higher. Which means if we want to push the piston inside, we have to continuously experience a bigger amount of force. So if we squeeze the gas by a little bit, we're going to experience a little bit of force. The more we're going to keep on squeezing the gas, the more force we're going to start experience on this handle. So there's going to be a proportional increase. So what this actually goes on to mean is that if we want to make the gas volume lower within the cylinder, tapped by the piston, then we have to physically do some force application, which means from an external source, maybe by our hand or maybe by another engine or maybe by some lever mechanism, by some physical entity, we have to do some application of force from the outside, and that piston should move in the direction of the force. This is what we mean. This is the scenario that force is applied from the outside and the motion is also happening in the direction of the force. This is what we describe as work done on the gas by an external source. So we don't usually say by an external source. We just usually, whenever we say the work done on the gas, it essentially means that work was fed onto the gas or into the gas from the outside. That essentially increases the total amount of energy of the gas at any point. If the gas had, let's say, some amount of energy stored within itself, if you wonder where does the energy come from, actually energy comes from the kinetic energy of the particles. If it's an ideal gas, or if it's not an ideal gas, there's this summation of or total amount of energy which comprised of the kinetic energy of the particles and also for the potential energy that exists between the particles due to intermolecular attraction forces, van der Waals attraction forces, so on and so forth. But not but. So the gas has certain amount of internal energy within itself. If we introduce some work from the outside, I mean, if work is done on the gas, then that total amount of energy is going to increase, which is considered as a positive work done on the gas. This is one scenario. The second scenario is that if by some procedure, uh, let's say, so I'm gonna write work done on gas when gas is compressed equals to pressure into delta V. In the same way, if in any case the gas itself expands, if you wonder why should the gas expand, the gas expansion can happen by a lot of different scenarios. One thing that we can do is that we can apply some heat from the surrounding of the cylinder, which can penetrate through the cylinder material and eventually heat up the gas molecules inside, and that will increase the speed of the moving particles, which can increase to a higher pressure. Rate of collision would increase, and individual collisions would actually happen at a much higher momentum change. So as a result, you can have a higher amount of force produced on the piston, and so in that case, the piston is going to start to move outwards. Whenever this piston has to move outwards, hear me out, they have to physically move this piston outwards. So there is a certain amount of motion would be happen because the piston has some mass. And also, for the motion of the piston moving outwards, it has to move away the atmospheric particles which earlier used to exist right over here. So if this piston slowly start to move outwards, the atmospheric particles has to push out from that exit position where the gas molecules would now exist for their own requirement of increased volume. So whenever a certain amount of gas increases in volume, we say that the object actually work is done by that gas. So I'm going to write this over here. Both of this calculation have the same formula. So I'm going to just write work done by gas. This happens when we go down a little bit. This happens when gas is expanded. It is also given by pressure into change of volume. So that also comes out as a useful formula. That is that. And এটুকু হচ্ছে আমাদের দরকারি জিনিস, নতুন নতুন জিনিস যেটা আছে। Apart from that, আমাদের work energy part chapter নতুন কিছু নাই। There are some significant problems relating the pressure scenario. So there are some pretty significant MCQs, and in very recent years they have started to give some paper 2 questions as well, using the pressure equation of P equals to H rho G and P equals to F by A. So the concept for pressure and buoyancy and upthrust, they were added recently in the syllabus. I did talk to you about buoyancy, right? Upthrust in your syllabus, right? Did I talk to you about upthrust?
Yes, sir.
Last please.
মানে তোমাদের এই সিলেবাসে বলছে আপট্রাস্ট নিয়ে আলাপ করছি তো?
Yes sir.
ওকে, সো আপট্রাস্ট রিলেটেড কিছু কোশ্চেন আমাদের পরীক্ষায় আসে। সো এগুলা খুব বেশি ডিফিকাল্ট না, এখানে জাস্ট একটা জিনিস বোঝা লাগবে। আমি ডাইনামিক একটা এক্সাম্পল তোমাদেরকে বলি, ডাইনামিক একটা এক্সাম্পল বললে তোমাদের জিনিসটা বোঝা ইজিয়ার হবে। যে I'm gonna say it to you and I want you all of you to understand. Let's say we have an object that has, let's say here we have some water. Let's say here we have some water. So এখানে কিছু পানি আছে। This container has, let's say, a pretty large amount of water. So I'm not saying about the depth. Let's say we have an object that is made up of iron. So let's say the volume of this iron piece is, let's say, 10 meter cube. And the mass of this iron piece is, let's say, 30,000 kg. So you can very easily find out it is nearly 3,000 kg per meter cube. I'm not sure if it's possible. I'm just assuming numbers. I'm trying to choose the mass or volume in such a way so that the density is more than 1,000, because I know solid iron is more dense than water. It is going to supposed to go into the water, and it's supposed to what is it called, submerge within a water, few amount of water. আচ্ছা, এর মধ্যে হাসান হাত উঠাইছিলা?
Yes, sir.
Did you get your question answered?
Yes, sir.
Acha, beautiful. So let's say we have some iron over here. How does this actually happen? Let's say whenever the iron is in air, considering the density of air is negligible. If you wonder why, the idea is that air has a density. The ideal density of air is actually 1.219 kg per meter cube, or 291 kg per meter cube. I actually forgot. It's about 1.3 kg per. I can actually show it to you. Why not?
Sir, can I ask one question about the previous topic, sir?
Yes, follow.
Sir, over here we wrote that pressure into volume, sir. Pressure into volume equals to force, na, sir?
1.225. Sorry. Pressure into
volume equals to force, na, sir? তাহলে work done হবে দিবে?
pressure into area হচ্ছে force.
Oh, okay, sorry, sir.
আমি এখানে actually একটা ভুল লিখছি, এটা force divided by area হবে। Pressure equals to force into area না, sorry, এখান থেকে তোমার ভুলটা হয়েছে, I'm sorry, I misled you, it's my mistake. Pressure equals to force divided by area. Work done হচ্ছে pressure into change of volume. এটাকে আমরা হোমোজেনিটি চেক দিয়েও দেখাতে পারি। ওয়ার্ক ডানের ফর্মুলা, ওয়ার্ক ডানের ইউনিট হচ্ছে জুল, প্রেসার ইউনিট হচ্ছে কি প্যাসকেল, ভলিউম ইউনিট হচ্ছে মিটার কিউব, তাই না? সো প্যাসকেলকে যদি ভাঙি তাহলে কি আসবে? নিউটন পার মিটার স্কয়ার, নিউটন পার মিটার স্কয়ার ইনটু মিটার কিউব। তো এখান থেকে আলটিমেটলি কি পাবো? নিউটন মিটার। সো দ্যাট অলসো গিভস ইউ জুল। তুমি হোমোজেনিটি চেক দিয়ে এটা প্রুফ করতে পারো, কোনো সমস্যা নাই।
Thank you, sir.
No problem. So এখানে জিনিসটা বলতেছিলাম, so let's say we have an object of this much. The area of density is only 1.225, which is very small compared to this. This thing is about 3000 kg per meter cube. So consider that the object for the time being in air is experiencing no upthrust. Let's say whenever we're going to start to submerge this iron cube inside water, as more and more part of this iron sphere gonna start enter under the water level, is going to display some amount of water equal to the volume of its own self that is under the water level. So the amount of volume of iron that has submerged under the water, that same amount of volume of water has to be pushed out. The weight of that pushed out water amount will come as upthrust. So this is the formula for upthrust. Upthrust is given by density of the liquid multiplied by volume of the displaced liquid, so volume of the displaced liquid multiplied by G. So whenever we're going to start to, if we start to slowly submerge this iron piece into the water, what's going to happen? The more it goes down, the more upthrust is going to experience. So as it's, if we have a scale over here that reads the absolute weight of this whole object, so we have a scale over here, that scale is gonna go down. So let's say there is a scale over here, this is a weight scale, and this whole thing is supported by some crane that goes up all the way up over here, and there are some copicals or pulleys over here, and we're going to roll this pulley and we're going to allow this whole thing to go down. So there is a display thing over here that tells you the actual weight of this whole thing. So let's say whenever it is in air, you're going to get around 300,000 Newton, a bit less than that because of 9.81, not exactly 10. But whenever we're going to slowly start to drop it, we're going to see that weight value is going to slowly decrease, because the downward weight is going to be constant, that is with 30,000 into 9.81. But as we slowly just start to submerge the sphere downwards, it's going to start to experience increased amount of upward force because of the upthrust. And when the entire thing would be underwater, it's going to have the maximum amount of upthrust force, which is going to be 10 meter cube into 1000 into 9.81. So 1000 is the density of water, 10 is its volume, 9.81 is 9.81. So if you multiply all of these things, how much you're going to get? 1 2 3 4 98100. You're going to get this much Newton of this much Newton, whereas the actual weight of this thing would be far more bigger. So essentially this is going to fall down and eventually it's going to submerge into the water. But when the whole thing will be, as the object will be slowly drowning into the water, we'll see this reading slowly reducing. Initially this reading would be equal to 30,000 into 9.81. How much that is, I don't know. You do that, so that would be the reading. But as we slowly pull the object down into the water, slowly but slowly the reading will decrease, and eventually as the object goes down all the way down, that reading would come back to a fixed value, which would still be a reading. It would not become weightless because the object is more dense than water, so it will definitely submerge within the water. That's scenario one, whenever we have object which is heavier than water. What if we have objects which are lighter than water? For example, let's say if we have a piece of wood, or if we have a bulk of wood. Okay, I'm going to take your question. Just give me a moment. So I'm going to go for this experience. Let's say we have a sphere of wood right over here. Okay, Hassan, you dropped your hand. Did you get your question answered?
না স্যার এই যে ড্রপ করছি
Acha. Anav, Amer, go ahead.
স্যার যত নিচে যাবে আপট্রাস্ট কি বাড়বে নাকি কনস্ট্যান্ট
বাড়বে। এই যে এখানে এই ফর্মুলা দেখো, upthrust formula is given by density of the liquid multiplied by volume of the displaced liquid. The further we're going to submerge the object into the water, the more water will be displaced, right?
Yes, sir.
So
বুঝছি স্যার।
okay, beautiful. So what happens if we have an object that is slightly less dense than water? Let's say we have a piece of wood that is less dense than water. Let's say we have a piece of wood over here that has a density of wood. Acha, wood and water seem to have, okay, water is going to be represented by L, wood is represented by W. Let's say the density of wood is, let's say 200 kg per meter cube, and water would be 1000 kg per meter cube. So let's say this sphere has a volume of, once again, 10 meter cube. Now, if I ask you to calculate that whenever I'm going to drop this object, how much volume of this wood will be actually floating? So can we calculate that? So try to understand this question. Density of water is 1000 kg per meter cube. Whenever we're going to drop this sphere of wood into water, it's going to slowly start to go down. As the object will go down, it will start to experience a bigger upward upthrust, because the more it submerges under the water, the more the upthrust will become. This object, which has a mass of about 200 kg per meter cube, has a mass of equals to 2000 kg. Therefore, its weight would be equals to 2000 into 9.81. That's going to be 1962. Zero. This many newtons. So this is the total weight of this whole thing. As this object is going to be dropped under the water, the further it will be dropped down into the water surface, it's going to start to feel lighter, more lighter. And there would come a certain point when the object would be somewhat half submerged in the water, and then the wooden sphere would not go any more down. It's not going to go down anymore. It's not going to be exactly half. Don't assume this is going to be exactly half. I would like to select this sphere individually, which I cannot. So I have to do Control Z, and select maybe into shade.
স্যার একটা কোয়েশ্চেন
Yes, go ahead.
স্যার আমরা যদি একটা পাইপ দিয়ে একটা বল, if you show like that was like a really soft ball which is a really low mass, ওইটাকে পাইপ দিয়ে একটা ওশানের ভিতরে ফেলে at a huge depth, ওই যে আপওয়ার্ড ফোর্স অফ দ্য ওশান অন দ্য বল, তখন কি ওইটা অনেক বেশি হবে?
No, অনেক বেশি হবে না। অনেক বেশি না হওয়ার কারণ হচ্ছে the upthrust force for any orientation of object always depends upon the pressure difference of the two surfaces. So upthrust can be actually given by the delta P multiplied by the A of the object. Delta P is actually the pressure difference at the lowest level and the upper level and the topmost level of the object. So that is the two different levels of the whole body, multiplied by the effective cross section through which the whole pressure is working. So if you have a spherical object that you push really deep down, so let's say now here are a couple of things to consider. Let's say this is the ocean level, this is the ocean surface. if you, let's say this is the bottom of the ocean level. So here is earth crust and this whole thing is ocean. Now, naturally, you should understand that actually water is almost incompressible, which means it takes a huge amount of pressure to make even the smallest amount of volume decrease for any amount of liquid water. Water is almost incompressible. But still, if we do consider water is somewhat compressible, which means that the deeper we're gonna go, we're gonna have some, we might consider that the density of water might increase. Now, the answer to your question in this case is not related to the depth of the ocean, it's related to the density change of the water. I'll tell you why. Here's the first thing. What is the absolute pressure at this point? It is dependent upon the atmospheric pressure plus the pressure produced by this amount of height of water. What is the pressure at this point? It is equal to the atmospheric pressure plus the pressure produced by this height of the water. So the deeper you go, the value of absolute pressure will be definitely bigger. No question there. It's absolutely true. However, if you have a spherical ball that has a fixed diameter and the difference between these two levels is not going to change, considering the ball can hold its shape, so the pressure difference is going to be less. So which means even if you place the object right over here, the amount of upthrust you're going to get, if you place the object right over here, the amount of upthrust you're going to get is going to be equal. However, here's the deal. If this ball is a hollow ball, let's say if it's a tennis ball, then in that case, the lateral pressure is going to increase by a lot. I mean, if this ball is not made up of by a solid metal ball, if it's not a very sturdy object, solid object, which can withstand a lot of force internally. I'm not talking about rubber, not squishy objects. I mean, obviously not hollow objects. Let's say just consider a solid metal ball and a tennis ball. If you apply enough force on a metal ball, it's going to deform, but it's not going to squash. Deforming means it's going to change the shape. So in one dimension, it's going to undergo squashing, but it's going to increase in the volume in the other dimension. So if you put it under a hydraulic press, if you squash it, it's going to slowly start to look like a toroid shape, or like the earth shape is going to become somewhat squashed in the top and the bottom, but it's going to widen up at the equator region. That's going to happen, but its overall volume is going to remain the same, provided the temperature is kept constant. But that's not the case for a table tennis ball. If you start to squeeze a table tennis ball from all direction with equal force, it can actually significantly squash it down, because the whole inside is actually made up of air. So, I mean, or if it's difficult for you to understand, you can also consider the table tennis ball to be a much more understandable version. Consider a very simple balloon. A balloon is very much similar like a table tennis ball, like a tennis ball. I'm saying table tennis ball. I'm sorry. A balloon is very much like a tennis ball, except for the thickness of the rubber part is much thinner. That's it. That's pretty much it. There's not much difference in there. So if the ball can hold its shape, then this diameter height would be same at any level. So the difference of this thing, I mean, the upthrust force is going to experience, is going to given by the difference of pressure in the top and the bottom level and the effective area. In this case, effective area is not the area of cross section. That is calculated by some other formula. I think its effective area is calculated by, there's a different set of formula to calculate that area. I'm not sure what is that. I have to look for it, but it's not the cross-sectional area, because the area actually varies. I mean, you have the maximum area right over here. Then as you slowly go on the upper side, your area is slowly becoming smaller and smaller. If you go further away from the equator region in the upward direction or in the downward direction, so the area would not be the maximum area. This is the average total area. There is a way to calculate that for objects which do not have uniform cross-sectional area. But if you have uniform cross-sectional area, for example, a cylinder object, a cuboid or a cube, you can have that. You can have a cross-sectional area which is equal to the side of one of the horizontal faces, which is perfectly all right. But for objects which do not have uniform shape, there is a specific formula for calculating for area. I'm not getting into the area calculation, but what I'm trying to tell you is that if the object can hold its shape, then the upthrust is going to be only dictated by the pressure difference of the top and the bottom level. But how much absolute pressure, but how much absolute pressure does the ball experience Is it
So the
submerged under the,
microphone, like,
I'm sorry, আমার ঝামেলা হচ্ছিল, sorry, I was replacing the microphone in my talking, sorry, এখন ঠিক আছে. So how much pressure should the ball experience as whole, I mean altogether, is depending upon at what depth the object is, but how much upthrust the ball is going to be experiencing is dependent upon what are the height difference between the topmost surface and the bottommost surface. Do you understand?
Yes, sir. বুঝছি।
I could give you some numerical values. For example, let's say over here, let's say this pressure is 100 unit. I'm not saying kilopascal or megapascal, whatever. Let's say this is 100 unit, and let's say at the bottom side this is 120 unit. So the difference, for the difference, we're going to getting a 20 unit pressure difference. If we go much deeper, it's possible that this thing could have been 1000 unit. In that case, this pressure is going to be 1020 unit. That's what you're going to experience. The absolute value of pressure is going to be more, but the difference of the pressure is going to be pretty much the same, which means you're going to come across with the same amount of upthrust.
Yes, sir.
Okay. This can significantly change if the liquid undergoes a significant volume variation, density variation, because you can see over here upthrust is also given by delta L into volume of the liquid into G. So volume of the liquid actually, volume of the displaced liquid, that is actually pretty much equal to the object's volume whenever we consider complete submersion. For example, a simple example, let's say if you try to consider the upthrust that exists because of air. In my example over here, I consider the air density to be nearly negligible because it was really less dense compared to iron, but air does have some density, and because there is a gaseous material, gaseous medium close to Earth's surface, it has the highest density, and as you slowly go further away, further up in the atmosphere, the density of air slowly reduces, and that gives rise to a significant problem. Is that gives us to a significant number of problems. Is that if you have a balloon that is at Earth's surface, it has and you fill it up with gas, and you are starting to get some upward force. You shouldn't expect that this force will exist for a very long time. I mean, the farther up the object will go, the air is going to become lighter. So density of air will become less, which means the upthrust is going to slowly become less. That is actually not going to happen only because of the density decrease. At the same time, but whenever the density will decrease, the pressure of the air will also decrease, and the balloon will also start to expand outwards. So balloon will also become bigger in volume. But it just so happens with respect to height, if you consider with respect to height, the density of the liquid, density of the air decreases more compared to the volume expansion of the balloon. So here's the deal. Let's say let me try to draw this for you. Let's say here is the Earth's surface. This is where atmosphere ends. This is a non-uniform atmosphere. So we have more air over here and less air over here. So I'm not sure if that figure actually makes sense. So something like that. So I'm trying to show you a relevant representation of mass distribution in a very raggedy way. So we have more density at the bottom side and we have less density at the lower side, at the top side. So whenever the balloon, let's say I'm going to show it over here. Let's say the balloon has a volume over here. As the balloon slowly goes higher, the pressure, atmospheric pressure decreases, which causes the density of the air also decreases. So as the balloon goes higher, it's going to start to become bigger in volume because of the lower pressure of the atmosphere. So its volume will increase, but the density of the air will decrease. The decrease of density will be more compared to the increase of volume. So if you experience half the density decrease, you're going to experience less than double of the volume increase. So your density decrease of the atmosphere for the same height gain would cause a volume expansion that is not exactly perfectly compensating. This is why as the object slowly goes up, there comes a certain point when the weight of the object and the upthrust of the object actually becomes equal, and the object cannot go any further up. In many cases, it's also possible that before the object actually can reach up to the maximum height, it will actually explode. Why? Obviously, because the balloon will start to expand. So there is this physical limit for how long the balloon material can hold its shape. So if the pressure if the pressure inside the balloon goes so high that the whole balloon border cannot contain the pressure anymore, then obviously the balloon is going to explode and the whole thing is going to get ruptured. That is also possible. So point that I'm trying to make is I'm actually drifted quite a lot from what I was trying to show you. So I was trying to solve this problem for you, that we are trying to put the object down, and we are asked that how much volume of this object would be under the water when the object no more submerges anymore. So how much volume in meter cube will be underwater? That's what we are trying to find out. So here is what we can do. Whenever the object will go down under, the total weight of this much volume of water would be equal to the actual weight of the object. See if you can appreciate this information, everyone. I'll say it again.
I didn't get it.
I'll say it again. When the wooden sphere would be allowed to drop into the water, and it will be allowed to submerge, but it will not submerge completely because it has a less density, it has significantly less density than water. As the wooden sphere will slowly start to go into water, it will start to experience increasing upthrust in the upward direction. So as more and more part goes underwater, it experiences more and more upthrust. There will come a certain point where a portion of the wooden sphere would be under the water and it will no longer go down, which basically means now we have reached an equilibrium. So the downward weight and the upward upthrust, they have become exactly equal to each other. That is the scenario. This is possible when the upthrust is equal to the weight of the object. So I'm going to write that equation over here. So upthrust equals to weight. We know how much was the exact weight. I calculate this thing to be 19620 Newton. How much would be the upthrust? Upthrust would be equal to the density of water, which is 1000, multiplied by the volume of the displaced liquid, which would be, by logic, the volume of the sphere that is under the water surface. This much volume. যতটুকু sphere পানিতে ডুবছে ততটুকু water volume সরানো হয়েছে. So that gives us, let's say, the volume of the displaced liquid multiplied by 9.81. So calculate this out from this equation. What is the value of the volume of the DL? Volume of displaced liquid volume কত হয়? Help us out.
Sir, W is the weight, sir.
Yeah, W is the weight. Yes.
0.929. Sir? 0.929 আছে 0.930 plus পরে 6 আছে স্যার
স্যার আমি জানি না স্যার, আমার এখানে স্যার 2 আসে কেন স্যার?
আমার 2 আসছে স্যার।
2 আসছে স্যার, আমি একটা 1 বসাই নি, আমি 91 লিখছি এটা।
This is going to be 2.0 meter. 2 meter cube. So 2.0 meter cube. Meter to na volume. We're trying to calculate volume. So this is going to be 2 meter cube. Now, the total object was 10 meter cube in volume. The total amount of submerged volume is going to be only 2 meter cube, which means this is not a very correct figure. The correct representation of this figure should have been maybe somewhat like this. A small fraction of the wooden piece is going to be underwater. I mean, out of the total 10 meter cube volume, 2 meter cube will be under water level, and 8 meter cube would be above water level. That's basically what I'm trying to show you, that this is basically how the submersion formula actually works. Interestingly, there are certain type of mechanisms, there are certain type of objects which actually can maneuver themselves within water. For example, fishes and submarines. How do they do it? How do fishes go to different level of water? Only by flapping their only by flapping their wings, are the wings, fins. Do they only do it by moving their fins? I mean, they go at different level of water. That's not supposed to happen. Well, it works because of what I just showed you over here.
Sir, fishes through the water's liquid oxygen. That's why they consume oxygen through their gills and increase their weight, sir.
No, that essentially happens. That's the biochemical process by which they by which they actually consume oxygen. But the way fishes can actually maintain a fixed level in water, for example, for those who have aquariums or you have come across to sea aquarium fishes, there is a certain number of fish called comet fishes, which are black in color, a bit like Rupchanda mas, but small. They have a very long dari type stubbards. They usually always stand at a fixed position in water. They don't move very much. Like goldfish, they don't move much, but they pretty much stand in one position and move pretty fast if they have to move. And there are many other fishes as well which can maintain a fixed level in a certain amount of water. Or for example, submarines, they can also maintain a fixed position within the ocean. How do they do it? The idea is very simple. If we want to keep something at a fixed position in a water body, we have to make sure of two things. First of all, the upward upthrust is perfectly balanced by the downward weight. Secondly, when this thing is achieved, the velocity should be zero as well. So you need to have some mechanism to control the velocity. You also need to have some sort of mechanism to control the forces. So in fishes, there are some things called air bubble hole, which looks like this. I don't know what those things are. I don't know the English of these things. There are some sort of air pocket which they fill up with air that they from the dissolved gases of the water, and they control how much air to be kept within this content within that cylindrical thing. By controlling their physical volume, bigger or smaller, they can control precisely how much upthrust do they experience. If they're trying to go upward, they increase the air within that thing and they will simply float upwards. This is also basically how a submarine works. Whenever, let's say, let me try to give you an idea. Let's say this is a submarine in the shore and people are boarding onto the submarine and there are a lot of people inside and now the submarine wants to go down. What does the submarine do? It starts to pump seawater within its ballast tank, which is not the actual body of the submarine where the people live. These are some sideways artificial tanks where the submarine can pump in seawater or pump out seawater as well. So it pumps in some seawater and makes the whole thing heavier than water. In this case, heavier than water means the combined density of the submarine becomes more than 1000 kg per meter cube. So the whole thing starts to sink down. Let's say the submarine wants to go rest at some depth, let's say 200-meter depth. So what we'll do, as the submarine approaches 200-meter depth, slowly the pump of the submarine are going to start flushing out the water, and they're going to do it in an automated way or by some critical calculation done by the onboard people, sailors. They're going to do it in such a way that whenever the submarine will reach this level, the pump would stop and it will be perfectly level at this position. If it undergoes some rush procedure, there can be some vertical propellers as well, which can actually control the exact level of this thing. I mean, other than pulling in water, blast water continuously, they can fill up the water at a fixed level and they can maintain their upward and downward motion with some propellers as well. But usually the propeller using is not done very commonly. Propellers are usually in the submarines are placed at the behind so that they can actually maneuver their boat left or right, not up and down. Up and down motion is always done by either pulling in water or pushing out water in the ballast tanks, which is always done in an automated algorithm. So the idea is that if some object has a total density less than water, it's going to float. Its upthrust will be bigger than its weight. If some object's total density is more than water, is going to sink within the liquid. I'm using the term total density for a reason. Understand what do we mean by total density? I'll give an example. I'll give an example. Let's say here is a water body, and there is a steel bowl that we have placed onto this water body, which has this much submerged over here, and it's not submerging into the water anymore. So let's say this is the shape of the steel bowl. We are seeing the long section. So we are seeing the side view. So this is all water. This blue line is iron, some alloy of iron. And what is this? What do we have here?
Sir, air, sir.
We have air. Beautiful. So here's the deal. When the steel ball has been submerged in the water and it is no longer going down under anymore, you have to consider that the total weight of this steel material and the air that exists within this level is equal to the upthrust upwards. So I'm going to write it this way. Mass of total steel bowl plus mass of air under water level. This is the total amount of mass that you have. You might wonder, why aren't you considering above this thing? Because above this part, that air is actually perfectly in the same horizontal level as the atmospheric air above the water body. So that air and that air are the same part. I'm going to tell you why I'm considering this part. So mass of the total steel bowl plus mass of the air under the water level. This is the total amount of mass that you have to balance into G. This should be equal to the upward force that you get out of this part of the whole thing. Now, upthrust expression আমরা essentially কি লিখি? Density of the liquid into volume of the displaced liquid into G. So G আর G যদি কাটা দেই তাহলে আলটিমেটলি আমরা পাচ্ছি হচ্ছে density of the liquid into volume of the displaced liquid. তার মানে হচ্ছে এই স্টিল বোলের টোটাল যতটুকু ভলিউম আছে তার মধ্যে এই ফ্র্যাকশন অফ ভলিউমের জন্য যতটুকু ওয়াটার ডিসপ্লেস হয়েছে ওইটুকু ওয়াটার মনে করা হচ্ছে এইটুকু ওয়াটার, মনে করা হচ্ছে এই ওয়াটারটুকু হচ্ছে এইটুকু, আমি ইচ্ছা করে কিউবিক শেপ রাখতেছি। সো লেটস সে এইটুকু হচ্ছে আমাদের ওয়াটার। এই ওয়াটারটুকুর যা ওয়েট, ডাউনওয়ার্ড ওয়েট, which is equal to the upward upthrust on this steel bowl because this much water was displaced, that is equal to the weight of the whole thing. Whole thing means of the whole steel bowl, equal to the weight of the whole steel bowl and the air within. If you have a bit of a confusion to understand that why did I consider this whole the air mass of the air for this much level, I'm going to show you a different example. The idea is that the density of iron is definitely far more than the density of water, but whenever the iron is hollowed out, that's what happens for a steel bowl. Inside that space, you have air. So as you slowly submerge in, you are submerging a composite object made up with iron and air. The more you put this thing inside, you are slowly introducing less and less iron and more volume of air, because the iron is actually thinned out in the shape of a bowl. It's a very thin sheet, but the actual volume of air that increases as you submerge the bowl more and more is actually significantly bigger, which means the total volume occupied over here by the bowl, or what we can call the total volume of the displaced liquid, was primarily made by the air. Air was actually occupying the volume that was responsible to move out. The reason air could push out the water is because of the presence of the steel barrier in between. If the steel barrier did not exist, then the water will definitely push out air and eventually the whole thing would become level. But because of the steel barrier, air can actually occupy the volume of the water. So here, your total object that is responsible to move out water amount is 2. There is a steel body and there is also air that is trapped within the steel body. Do you understand?
Yes, sir.
Okay, so if I want to consider the composite density of the steel bowl, I can write, আচ্ছা আমি composite density না লিখে composite density distribution জন্য না দেখাই, আমি actual একটা example দেখাই। Let's say this is a ocean surface, let's say this is a submarine, আচ্ছা even better, let's say this is the propellers of the submarine। মনে করি এই সাবমেরিনের ভিতরে এইটুকু হচ্ছে ব্লাস্ট ট্যাঙ্ক, মানে হচ্ছে এই এইটুকু হচ্ছে এইটুকুর মধ্যে আমরা ব্লাস্ট ট্যাঙ্কের ভিতরে পানি ভরতে পারবো, আর এইটুকুর মধ্যে মানুষ সব ঘোরাঘুরি করছে, ইঞ্জিন সবকিছু আছে, ঠিক আছে। এখন সাবমেরিনের টোটাল এক্সটার্নাল ভলিউম হচ্ছে পারফেক্টলি এইটুকু, এর মধ্যে এইটুকুতে আমরা অপশনালি পানি ভরতে পারবো, আর এই স্পেসটুকু হচ্ছে বিভিন্ন রকম যন্ত্রপাতি দিয়ে ভরা, মানুষ আছে, বাতাস আছে, সবকিছু আছে, ঠিক আছে। The way a submarine is designed, the way it is designed, and the way these portions and volumes are made in such a way that without any human being inside the submarine, if you fill up the whole thing with water, the total density of the submarine would be more than the density of water, which means if you fill up this whole thing with water, if the entire blasting is filled up, your total mass of the submarine divided by the total volume of the submarine would be equals to the density of the submarine, which should be somewhat bigger than the density of the water, so that the submarine could actually sink down. If you fill up this thing with more crew, then your crew actually provides a significant amount of mass, so that you don't have to fill up the blast tanks completely, which actually gives you a bit more advantage. So that's how the submarine works, because the total amount of, whenever it is underwater, the total amount of volume of water that the submarine actually displays is actually fixed, is equal to the outer shell volume of the submarine. The key thing that the submarine changes is actually the amount of mass that it has within itself. Whenever it pumps water in, it increases its mass. So and volume formula কি, volume formula হচ্ছে mass by density formula হচ্ছে mass by volume। ডুবতে হলে আমাদের কি করতে হবে, mass of the submarine should be bigger than the mass of the water। ভাসতে হলে কি করতে হবে, mass of the submarine should be less than the density of water। That's the basic idea. So whenever it pulls in water, it increases the mass within the submarine body, the volume remains the same, and as a result, as the moment it becomes heavier than water, it slowly starts to sink in. And then if it wants to maintain a fixed depth underwater, that's when it flushes out a very specified amount of water, so that the density of the submarine becomes exactly equal to the density of the water. At that point, the submarine can maintain a fixed depth under the water, and then it can maneuver and go places where it wants to go. এই পার্টটা বুঝে গেছে কিনা?
Yes, sir.
Sir, একটা question, sir. If
Hello.
the density of the submarine is equal to the density of water, how can it like stay at a certain level below the water? It's gonna be somewhere like at the water, top of the water level, right, sir?
No. It doesn't have to be at the water level. I'll tell you. I'll give you a very simple explanation for what you just asked. Very simple explanation. Hear me out. Whenever any object reaches terminal velocity, does the
Yes, sir.
object experience zero force?
No, sir.
But does the object maintain its terminal velocity?
Sorry, sir.
Whenever an object reaches terminal velocity, the object does not experience zero force. The object experiences zero resultant force. But
Yes,
there
sir.
are usually equal and opposite forces which balance each other out. That's what we define as terminal velocity, right?
Yes,
So,
sir.
if you can reach upthrust equals to weight situation where you are stationary, is there any reason for you to move up and down?
No, sir.
I think that makes answer for yourself.
Okay, sir.
This is also the similar mechanism by which scuba divers actually work. I mean, many of you have seen that usually human beings, the way us human beings actually we are designed. I mean, people who know how to swim can float. People who don't know how to swim cannot float. Why is that? I mean, are people who cannot swim more dense?
No, sir.
This word dense has a meme-based meaning. I'm not going for that. I'm meaning literal density. The reason is is that whenever we move our hand and we create disturbance in water, that allows us to get a little bit of additional upward force. So people who know how to swim, they move their hand and feet under the water. Let's say someone is floating vertically, so just floating vertically, and they are just moving. They are not floating vertically, being still. That doesn't happen. They have to continuously move certain portions of their body, and that motion gives them a sort of movement related upward force. It's very much like the way the airplane moves forward. I mean, whenever the airplane is pulled forward by its propellers or by its jet engine, or pushed forward by using its wings, it generates an upward force. Similar thing. So people actually do that by continuously gaining that upward force. That's why we human beings have to continuously move our body. If you drop a person who cannot move their body parts into water, they'll definitely sink, no matter how good of a swimmer they are. So moving can get us the additional force, pretty much like the way propeller works. It pushes water in one direction to get a force in the opposite direction. That's how us human being can also float into water. But there are certain other animals who naturally can float in water. For example, most animals, for like what, like you name it,
Crocodile.
crocodiles can also, crocodiles are very much like submarine mechanism. They have a very precise understanding for how much water that they need to put in, or how much breathe in they have to do, or how much breathe out they have to do, just to change their volume of their belly, to make sure that whether they're underwater or they are floating at the water, or they have to go jump out of the water. They know this very well. So pretty much in the same way, I mean, if you want to put it in some manner, for example, let's say in the same way that we human beings learn to walk or stand up on 2 feet, standing up 2 feet is a very difficult mathematical problem. For those of you who don't know, learn this. If you ever try to make a certain biomechanical or mechanical device that want to stand up on its own, you have to go through a lot of trial and error and a lot of problem solving. I mean, making a standing up robot is not an easy thing. I mean, you can make a standing up robot, but it should be able to walk, jump, and do tango sort of dance. It's a difficult thing. It's a very difficult thing. But we human beings learn this in a pretty small amount of time when we were young, because the algorithm in our brain, the biological thing that is inside our skull, that learns what muscles to pull and what muscles to give up, and in what sequence the muscles have to be maintained, of the whole body. I'm not saying only for the feet, all the way from the heel all the way to our neck, all the way up. It knows for every muscle movement that for which orientation of our body, which muscle have to be in what kind of tension level, to make sure we are not falling over. So that whole thing is learned by our brain. It's pretty mesmerizing. We don't know this stuff. This stuff doesn't happen in our known brain. It is our automated. It is done by our automated nervous system. So to be honest, whenever people say that my brain is no good, every people's brain is good. It's just not for understandable way or not. So I'm getting into a different type of discussion. Not want to go there. বুঝে গেছে কি?
Sir.
Yes, sir.
Yes, sir.
Sir, can you swim, sir?
No.
Oh. Okay.
ফ্লোটিং এর ব্যাপারটা বলতে পারতেন।
আমি কিছু একটা ধরে বেঁচে থাকতে পারি, মানে হচ্ছে সেটা ধরে তো সবাই বেঁচে থাকতে হয়। That actually sounds pretty stupid. The thing is, if I can hold on to something, I can make myself horizontal, and I can keep myself horizontal for an indefinite period of time without getting tired. I tried this for like 40 minutes or so, but the moment I let go of that thing, my head starts to sink in. Which what I believe is that my leg part portion have learned how to swim, but my hand and the torso part didn't learn how to swim. Sort of like that. Does it somehow make sense?
No, sir, not making sense.
মানে হচ্ছে আমাকে যদি হরাইজন্টাল পানিতে ছেড়ে দেওয়া হয়, আমার পা গুলা ভেসে থাকতে পারবে, কিন্তু আমার মাথাটা ডুবে যায়। মাথার সাইডে আমাকে কিছু একটা দিয়ে ঠিকা দিয়ে রাখতে হয়।
পা উপরে চলে যায়, মাথা নিচে চলে যায়।
হ্যাঁ। Anyway, maybe a bit more practice I would learn, or maybe if maybe I would never, or maybe I'll die in water. I don't know. Let's not get there. আমি এইটা রিলেটেড তোমাদের ওয়ার্ক এনার্জি পাওয়ার বেসিস রিলেটেড তোমাদেরকে একটা কিছু প্রবলেম দেখাইছিলাম। তোমাদের একটা হোমওয়ার্ক দিছিলাম না বেশ কিছুদিন আগে?
Sorry, sir. Homework করি নাই, sir.
দুটো
কি homework ছিল?
এমসিকিউ পেপার দিছিলাম আমি তোমাদেরকে।
জি স্যার, ওটা
Sir, দুইটা, sir.
বুঝতেছিলাম না।
তাহলে ওই এমসিকিউ দুটো আমি এখন করাবো, দুটোই এখন করাবো আমি তোমাদেরকে। এমসিকিউ দুটো কোথায় আছে?
গ্রুপে তো আছে।
গ্রুপে আছে?
Yes,
জি
sir.
স্যার।
Messenger group, sir.
আচ্ছা, আমি প্রবলেম দুটো বের করতেছি। একটা হচ্ছে এই প্রবলেমটা। I'm gonna give you some time.
এটা অনেক আগেই দিছিলেন স্যার।
তোমরা করছো এটা? আমি তো ডিসকাশন করি নাই।
সলভ করছিলাম কিন্তু হারাই ফেলছি যেখানে সলভ করছিলাম।
তাহলে আরেকবার সলভ করো। I'm gonna give you some time. So I'm placing this within your view. তোমাকে সবাই পুরোপুরি দুটো কোশ্চেন দেখতে পারতেছো?
জি স্যার, দুইটাই দেখা যাচ্ছে স্যার।
কিন্তু স্যার এখন দুটো ওভারল্যাপ।
I think this is better. Okay. Try these two questions. I'll give you 5 minutes. I'll be back in 5 minutes. So question number 16 can be solved in two different ways. We can go by angle, or we can go by not angle. Okay, try to understand. An escalator is 60 meters long and lifts passengers to a vertical height of 30 meters as shown. To drive the escalator against the force of friction, there are no passengers requires a power of 2 kilowatt. The escalator is used by passengers of average mass 60 kg, and the power to overcome friction remains constant. How much power is required to drive the escalator when it is carrying 20 passengers and is traveling at 0.75 meter per second? So the escalator is traveling at 0.75 meter per second. The direction of the escalator to move is this way. If the escalator is moving at 0.75 meter per second, what is the rate of vertical height? I'm going to do the maths, all of these maths for 1 second, so that the problem solving becomes easier. Have a look. In 1 second, it moves diagonally by 0.75 meter. I want to find out how much should this be. The question tells me when this is 60, this part is 30. So I'm going to go by equal ratio problem. So 0.75 divided by 60 should be equals to x divided by 30. So therefore, x equals to how much? 0.75 divided by 2 gives me 0.375. So in 1 second, the vertical height gain of the escalator is 0.375. So how much GP should be provided to the people? 60 passengers, 60 kg passengers, 20 passengers, that is 1200 kg. I'm doing only for the passengers here. Into 9.81 into 3.75. দেখো এটা বুঝা যাচ্ছে কিনা বলবান?
0.375 এটা কিসের স্যার? ও মানে x মানে height.
হ্যাঁ, ভার্টিক্যাল হাইট। সো এটা করে দেখো কত আসে। 4.41, 4.5. 4414.5 joule. So this much GP should be provided to the passengers every second. So this many joule per second is required for the passengers. The accelerator on its own requires 2 kilowatt. So total power requirement would be equals to 4414.5 plus 2000 watt. That is about 6.4 kilowatt. This is the correct response. Important
Sir,
part, I did the math for 1 second. Hello.
Sir, 2000 কেন add করলাম স্যার আমরা?
Because by default the escalator requires 2 kilowatt friction, 2 kilowatt for its own.
Thanks, sir.
Additional to its own power, we have to lift up the people. I calculate the whole thing for 1 second. That's one way to go for it. There is another way. We can also do this math by the formula P equals to FV. Because the question says that the lift should be going up at a constant speed of 0.75. So if you want, we can also use this, but we cannot directly use 0.75 for our requirement. We have to find out how much 0.75 meter per second in this direction would mean in this direction. I did the math over here. So 0.75 meter per second যদি এখানে হয়তো এই স্পিডটা কত আসতো 0.375 meter per second. এই ক্যালকুলেশনটা কি বুঝো?
না স্যার বুঝি নাই স্যার, সেটা আবার বলুন স্যার।
If you use trigonometry and use opposite by hypotenuse, you're gonna come up this angle to be 30 degree.
Okay, sir. Yes, sir. Understood.
And if you consider this triangle, where this direction speed is 0.75 meter per second, what should be the speed in this direction? 0.375 meter per second. So you have to continuously lift up the people vertically for 0.375. Now, if you want to find out the required power for that, that will be given by FGV. FG is actually mg into the V, which basically gives you 60 into 20 into 0.375. Pretty much the same thing. You get 4414.5 watt, and then the total power would be equals to 4414.5 plus 2000 gives you 6414.5 watt. এভাবেও করা যায়, আইদার পুরো ম্যাথটাকে 1 সেকেন্ডের জন্য জাজ করে করা যায়, অথবা তুমি ডিরেক্টলি স্পিড দিয়েও করতে পারো। বুঝা গেছে বলবান?
আমরা যখন MGH ইউজ করে জুল বের করলাম, ওটা হচ্ছে 1 সেকেন্ডের জন্য।
কোনটা?
ফার্স্ট পার্টটা MGH দিয়ে যে আমরা 4414.5 বের করলাম, ওটা হচ্ছে জুল পার সেকেন্ড।
For 1 second, yes, I did the whole math for 1 second because I want to get the power, which means all of my joule requirement would be for 1 second. So I calculate the whole math for 1 second so that I could directly add the power with this thing. এটা না করে আমি পুরোটা ইন্ডিভিজুয়ালি টাইম বের করে করতে পারতাম যে টোটাল 30 মিটার রাইজ করার জন্য কতটুকু টোটাল জিপি গেইন হবে, এই টোটাল জিপি গেইন করার জন্য মোট কত সেকেন্ড ধরে ট্রাভেল করতে হবে। ফর এক্সাম্পল, if I want to go by that other method, I could also go by this. I'm gonna write it over here, let's say. So let's say পুরো লিফটটা মনে করো বটম থেকে একদম টপ পর্যন্ত ওঠার জন্য টোটাল টাইম লাগবে কতক্ষণ? 60 divided by 0.75, ঠিক না? এটা বুঝতেছো?
Yes, sir.
এটা কত আসে দেখো, 80 সেকেন্ড। 80 সেকেন্ড টাইম লাগবে। এখন এই 80 সেকেন্ডের মধ্যে আমার টোটাল জিপি গেইন হবে কত? 80 সেকেন্ডের মধ্যে টোটাল জিপি গেইন হবে হচ্ছে এইটুকু, না 80 সেকেন্ডের মধ্যে টোটাল জিপি গেইন হবে হচ্ছে 60 passengers into 20, that's the total mass, into 9.81 into 30, the total height, total vertical height. Total GP gain এতটুকু হলো, এটা তুমি বের করলা। Therefore, power required for the passengers সেটা হবে কত? এই পুরোটা ডিভাইড বাই 80 সেকেন্ড। ওখান থেকে তুমি যদি ক্যালকুলেট করো ওখান থেকে তুমি 4414.5 এটাই পাবা। করে দেখো কত আসে।
জি স্যার, এটাই আছে।
বুঝছো? সো
হ্যাঁ স্যার।
যদি আমি 1 সেকেন্ডের জন্য না করে পুরোটুকুর জন্য করি, তো পুরোটার জন্য করতে হবে, সেক্ষেত্রে আমাকে টাইমটাকে ক্যালকুলেট করে বাই করে নিতে হবে, তারপর বাকিটা অ্যাজ ইউজুয়াল ফলো করলে হবে। সো এটা আসবে, ওটার সাথে 2 কিলোওয়াট যোগ করে দিতে হবে, দ্যাটস ইট। বুঝে গেছে সবার?
স্যার সেকেন্ড মেথডটা বোঝা যায়নি স্যার, ফার্স্ট মেথডটা বুঝা গেছে স্যার।
এটা
মানে স্যার এটা বোঝা গিয়েছে স্যার, মানে স্পিড রেটটা বোঝা যায়নি স্যার।
আচ্ছা, the lift has a linear speed along this slanted path that is 0.75 meter per second, as the question tells us. এই যে এখানে 0.75 meter per second।
ইয়েস স্যার।
তাহলে টোটাল 60 মিটার কভার করতে কতটুকু সময় লাগবে? Speed equals to distance over time, time equals to distance over speed, distance হচ্ছে 60, speed হচ্ছে 0.75, gives you the time 80 সেকেন্ড। মানে টোটাল সবগুলো প্যাসেঞ্জারকে নিচ থেকে উপরে উঠে টোটাল 80 সেকেন্ড টাইম লাগবে। বুঝছো?
ইয়েস স্যার।
এই 80 সেকেন্ডের মধ্যে টোটাল প্যাসেঞ্জারদেরকে আমি মোট কতটুকু জিপিএ দিব? 20 জন প্যাসেঞ্জার অন এন এভারেজ 60 কেজি ওয়েট সবার, তাদেরকে উঠাইছি কতটুকু ভার্টিক্যাল হাইটে? 30 মিটার ভার্টিক্যাল হাইটে উঠাইছি, ঠিক না? টোটাল জিপি সাপ্লাই কত? এতটুকু।
ইয়েস স্যার।
এই জিপি টুকু কতটুকু সময় সাপ্লাই হয়েছে? 80 সেকেন্ডে।
ইয়েস স্যার।
ডিভাইড করলে পাওয়ার আসবে।
ইয়েস স্যার।
পাওয়ারের সাথে আবার লিফটের অরিজিনাল পাওয়ার অ্যাড করে দিলে টোটাল পাওয়ার পাওয়া যাবে। বুঝছো?
ইয়েস স্যার। থ্যাংক ইউ স্যার।
Sure, no problem. আচ্ছা, এটা গেল এটা। এটাকে আমরা সলভ করব। How do you solve this one? A small mass.
স্যার কি হবে?
এটা কারেক্ট অ্যান্সারটা আমি ভুলে গেছি।
স্যার এটা যে পি থেকে কিউ এ নামলে তো স্যার জিপি 1/4 কমবে।
তাহলে স্যার এ হবে না স্যার আনসার?
I don't know. You tell me.
স্যার পি তে তো হাইয়েস্ট গ্র্যাভিটেশনাল পোটেনশিয়াল এনার্জি, টি তে হাইয়েস্ট কাইনেটিক এনার্জি, তো টু লুজ 1/4 অফ দ্য গ্র্যাভিটেশনাল পোটেনশিয়াল এনার্জি, ওইটার ডিস্টেন্স ফ্রম টি 3/4 হবে না?
এখানে কি তুমি ডিসটেন্স দেখতেছো?
না স্যার, এই যে ভার্টিক্যাল
You only have the instantaneous speed of the particle for defined positions. You have no mention of how much vertical height it has fallen or how much time has passed. None of these information are provided to you. সবগুলো পয়েন্টে ইনস্ট্যান্টানিয়াস স্পিড গুলো শুধু দেওয়া আছে।
ও স্যার, তাহলে কাইনেটিক এনার্জি বের করতে হবে।
এক্স্যাক্টলি।
তারপর যেটাতে পুরা কাইনেটিক এনার্জি বের করতে হবে, তারপর প্রত্যেকটা পয়েন্টে কাইনেটিক এনার্জি বের করতে হবে, তারপর ক্যালকুলেট করতে হবে।
এক্স্যাক্টলি। সো বলবান দেখো, এখানে একটা জিনিস ওটা বলে দিছি ইচ্ছা করে, এটা খুব ভালো করে খেয়াল করো, নট টু স্কেল, যাতে করে স্টুডেন্টরা এটা এখান থেকে ভার্টিক্যাল হাইট গুলোকে ইচ্ছা মতো ভার্টিক্যাল হাইট জাজ না করে, because this figure is not drawn to scale. Intentionally it is not drawn to scale. So have a look. This is how I try to solve the problem. There might be other ways, easier ways, I don't know. Here's the thing, the question says a small mass is placed at point P on the inside surface of a smooth hemisphere. Smooth is very important. It means there will be no loss of energy. It is then released from rest. So a position rest is zero. When it reaches the lowest point T, its speed is 4 meter per second. আচ্ছা, আমি ধরে নেই আমাদের ম্যাসটা হচ্ছে মনে করো m। আমি যেটা এটাকে 1ও ধরতে পারতাম, আমি ইচ্ছা করে m ধরলাম। 1 ধরলে ম্যাথ আরো ইজিয়ার হয়ে যায়, শুধু সংখ্যা নিয়ে কাজ করতে হয়। আমি অ্যাকচুয়াল সলভ করার সময় 1 দিয়ে করছিলাম, বাট তোমাদের বুঝার জন্য আমি m ধরলাম। তার মানে হচ্ছে আমার এই পজিশনে কাইনেটিক এনার্জি হবে কত? হাফ m 4 স্কয়ার, ঠিক না? প্রমাণ খেয়াল করো, কাইনেটিক এনার্জি এর টি হবে কত? হাফ m 4 স্কয়ার। তাহলে এটা কত আসে? 8m। কাইনেটিক এনার্জি এট s কত আসবে? হাফ m স্কয়ার, তার মানে হচ্ছে 9/2m। কাইনেটিক এনার্জি এট r কত আসবে? হাফ m 2 স্কয়ার, মানে হচ্ছে 2m, কাইনেটিক এনার্জি at q আসবে হচ্ছে হাফ m 1 স্কয়ার মানে হচ্ছে m/2। এই হিসাবটা কি বুঝছো সবাই? বলবান
Yes.
এখন যেহেতু আমাদের স্ফিয়ারটা স্মুথ, does this not essentially mean that kinetic energy at this point must be equal to gp at this point?
Yes, sir.
তার মানে হচ্ছে kinetic energy at p equals to 0, which means gp at p should be equals to 8m. এটা কি বুঝো? এই লেখাটা বোঝাচ্ছে? This is logic. The question is asking us, at which point has the mass lost potential energy by 4? So E/4 potential energy lose করছে কোন পয়েন্টে? E/4 মানে কতটুকু? দেখো, যতটুকু পটেনশিয়াল এনার্জি লুজ করবে ততটুকুই কাইনেটিক এনার্জিতে কনভার্ট হবে, ঠিক কি না? এটা তো বুঝো। কারণ যেহেতু আমাদের স্মুথ স্ফিয়ার, হেমিস্ফিয়ার, so কোনো রকম এনার্জি লস নাই, there is no energy loss, so the amount of kinetic energy change would be exactly coming from the decrease of potential energy. If the sphere has lost E/4 potential energy, it means delta gp downwards should be equals to E/4, which means delta k upwards starting from 0 should be also equals to E/4, ঠিক না? এখন according to the question, এই পয়েন্টে এই amount of energy এখানে কোশ্চেনে বলে দিছে, have a look at this question. What is E? The mass of potential energy E is expressed by E. তার মানে হচ্ছে এই পজিশনের যে 8m যে ভ্যালুটা, এই 8m ভ্যালুটাকে ডিফাইন করা হচ্ছে E দিয়ে। তাহলে E/4 কত হবে? 2m হবে। সো যে পয়েন্টে 2m জিপি লুজ করছে, এক্স্যাক্টলি ওই পয়েন্টে কেইও কত হবে? 2m হওয়ার কথা না? বুঝো কোশ্চেনের ওয়ার্ডিংটা খেয়াল করো। At which point the mass has lost E/4 potential energy? The location where it has lost E/4 potential energy, it would have also gained E/4 kinetic energy, which means you are trying to find out the location where the kinetic energy of the ball should be 2m. And এখানে দেখো কোনটাতে কোন পয়েন্টে 2m হইছে, এই পয়েন্টে কাইনেটিক এনার্জি 2m হইছে, দেখতেছো?
Yes, sir.
রেসপন্স হচ্ছে r। আমি যদি ম্যাথকে 1 ধরে নিতাম তাহলে আমার ম্যাথটা আরো ইজি হতো। কিভাবে ইজি হতো আমি তোমাকে বলি। The way I actually solve this problem, আমি কিভাবে এটা সলভ করতে চাই। আচ্ছা, এই আমি এই পসিবিলিটি কি বুঝে গেছে সবার? কি আলাপ করলাম এখানে?
Yes, sir. Thank you, sir.
There is a little bit of back and forth over here. You have to understand that the change of GP to K would be equal. The amount of K at the bottom should be equal to amount of GPE at the starting. This is a very important understanding that you have to apply. And then from there you have to find out E/4 amount of GP loss should also mean E/4 amount of K gain. And then you have to find out the correct answer. আমি 1 ধরে যেভাবে সলভ করতে সেটা একটু দেখাই। Oh, all of these things actually showed up. So let me just erase this. I cannot grab this. Why? Can grab this. So I consider the mass of the object to be 1. So এখানকার আমার টোটাল এনার্জি ধরছিলাম হচ্ছে আমি 16 ইউনিট। তাহলে এই পয়েন্টের জিপিইউ হচ্ছে কত? 16 ইউনিট, 16 তো না, সরি 8 ইউনিট। এই পয়েন্টের জিপিইউ হচ্ছে 8 ইউনিট। আমাকে বাই করতে হবে হচ্ছে কোন পয়েন্টের কেই 2 ইউনিট। সো এই পয়েন্টের কেই হচ্ছে হাফ ইন্টু 1 ইন্টু 1 স্কয়ার 1/2। এই পয়েন্টের কেই হচ্ছে হাফ ইন্টু 1 ইন্টু 2 স্কয়ার 2 এই পয়েন্টের কে হচ্ছে 9/2 so essentially this was my answer আমি এইটুকু লেখা লিখে তারপর ম্যাথটা সলভ করছিলাম I did all the thing in my head and that's how I went for it. It's not important that you have to consider the mass equals to 1. I could do it because I knew it could be done, but for your cases you shouldn't make it as a practice unless you know for a fact that why you can consider that. I did this for the sake of an easier calculation, but if you understand this thing better, you can go for the M thing and go for this thing. Interesting for you to know that both of these questions showed up in one specific year, and these two MCQs are not easy to solve. If you ask me, they require some significant thinking and rethinking. এবং এই কোশ্চেন পেপারটাতে মোট এরকম কোশ্চেন ছিল মনে হয় তিনটা না চারটা মনে হয় there are some big questions in the question আমি ইয়ারটা ভুলে গেছি
Sir, did your students of that year told you about this, or how did they work on this?
মানে যারা পরীক্ষা দিছে
Yes, sir.
এটা মনে হয় আমাদের ভ্যারিয়েন্টে ছিল না এটা সম্ভবত 2-1 এ ছিল মনে হয় সো 1-1 এ বা 1-3 তে ছিল I think anyway আমি জিনিসটা বলতে যাচ্ছি যে ওই চারটা কোশ্চেন ছাড়া বাকি পুরো পেপারটা সলভ করতে আমার সময় লাগছে হচ্ছে আবার 15 না 17 মিনিটের মতো রেস্ট অফ দা হোল পেপার এবং আমি এমসিকিউটা ভুল করছিলাম ক্যালকুলেশনে ভুল করছিলাম আমি 39 পাইছিলাম এই পেপারটাতে actually rushed so my bad anyway ইঞ্জি পার চ্যাপ্টারে বেসিক্যালি থিওরিটিক্যাল পোরশন আর কিছু নাই সো এরপর আছে হচ্ছে আমাদের ইলাস্টিসিটি চ্যাপ্টার আমি ইলাস্টিসিটি চ্যাপ্টারটা আজকে শুরু করতেছি
স্যার
বলো
স্যার আমাদের স্কুল এক্সামের